I am David Falliano, a postdoctoral researcher at the Polytechnic of Turin. In the contribution I am going to show you, I'll present some results of an ongoing research focused on a very interesting special concrete, namely foamed concrete. In particular, the title of this presentation is Strategies to Increase the Compressive Strength of Ultra-Lightweight Foamed Concrete. The context is that of cellular concrete and in particular foamed concrete that belongs to the wider category of lightweight concrete. As illustrated on the slide, the elements forming foamed concrete are simples, chips, and easily availables: cement, stable foam, fine sand, and, if necessary, additives. The preformed foam, mixed with the cement paste, give rise to the development of a system of air voids in the material microstructure. The peculiar characteristics of foamed concrete elements are those common to all cellular systems: thermal insulation, especially when low density are employed, sound absorption, good resistance against fire, flotation, obviously for density lower than 1000 kg per cubic meter, but above all, lightness. Therefore, foam is the ingredient that characterizes these cementitious materials and is formed by trapping pockets of a gas, in most cases air, in a liquid, in order to obtain liquid foams, or in a solid, so as to obtain solid foams. Liquid foams are composed by a solution of water and surfactant expanded with air. Surfactant molecules, which are amphiphilic, prefer to be present at the interface air fluid, and they arrange themselves so that the tail groups are in contact with the air, while keeping the head groups within the liquid. They play the fundamental role of increasing the lifetime of the foam. Obviously, density plays a crucial role in defining the properties of foamed concrete. An increase in the volume of foam in the mixed proportion will lead to a decrease in the density of the cementitious material, since the air bubbles will occupy a greater part of the volume. Based on the density, foamed concrete is used in different ways. In the density range between 300 and 600 kg per cubic meter, foamed concrete is used in flat roofs with relative slopes, subfloors, cavity fills, insulation of raceways, thermal insulating blocks, fire protection of steel structure, and, in general, any type of filling where high thermal insulation is required. In the density range between 600 and 900 kg per cubic meter, in substrates for industrial floors, blocks and slabs for building envelopes and partitions, slab for ceilings, void filling. In the density range between 900 and 1400 kg per cubic meter, in prefabricated and cast in situ walls for both load-bearing and non-load-bearing functions, blocks and slabs. In the density range between 1400 and 1800 kg per cubic meter for structural purposes, where higher strength is required. These different field of applications are due to the fact that, if, on the one hand, the increase in the porosity of the material is associated with improved physical properties such as thermal insulation, acoustic absorption, fire resistance, lightness, which are, in many respects, characteristics of absolute importance in the building sector, on the other hand, the increase in porosity is accompanied by a significant reduction in mechanical performance. Evidently, the utopia is to obtain a material characterized by all the physical properties that characterize lightweight foamed concrete, associated, however, also with good mechanical strength. All this has led many researchers to concentrate their efforts to determine ways to improve the mechanical properties of ultra-lightweight foamed concrete, with a targeted high density lower than 500 kg per cubic meter, without worsening the lightness. This contribution fits into this field of research and presents some strategies to improve the compressive strength of ultra-lightweight foamed concrete. Compared to ordinary concrete, the mixed design of the foamed concrete is much more complicated because, in addition to conventional parameters such as the water-to-cement ratio, the granulometric assortment of aggregates, the amount of cement, the mineral additions, its properties are influenced by other factors: the nature and the amount of the foaming agent, the mixing process, namely the type of the mixing intensity, and the duration of mixing. In the relevant literature regarding the nature of the foaming agent, it is shown that the best results in terms of compressive strength are associated with the use of a protein rather than synthetic foaming agents. Therefore, the easiest way to produce a foamed concrete characterized by greater strength is to use protein foaming agent. However, with the same foaming agent, what strategy can be used to improve the compressive strength? There are two different types of strategies: modify the mix design, modify the mixing process. In the following slides, I will show you the experimental results related to the application of these strategies on ultra lightweight foamed concrete with a target ray density of about 400 kg per cubic meter. All the specimens are prepared using Portland cement, a foam characterized by a density approximately equal to 80 grams to liter, generated with a protein foaming agent called foaming C, and a water to cement ratio equal to 0.3. The tests are performed on cubic specimens of 5 cm height. For each different curing condition analyzed, namely air, wrapped in cellophane, and water, 3 different samples are tested, and the reported compressive strength is the average value of the 3 experimental findings. Other parameters of interest will be reported in the next slides. As far as the first class of strategy is concerned, an unusual way to improve the compressive strength of ultra-lightweight foamed concrete is to increase the consistency of the fresh paste, providing, for the mix design, the presence of an appropriate viscosity enhancing agent. The mixing intensity of the vertical mixer was set at 1200 revolutions per minute. The photos show the significant fresh state differences between the two ultra-lightweight cementitious pastes. As you can see from the comparative histogram, a higher consistency generally corresponds to a higher compressive strength. A justification for this result may be given in terms of air void distributions and dimensions. Indeed, the air bubbles in the more consistent paste are more uniformly distributed and are characterized by significantly smaller dimensions. This is due to the higher confinement pressure to which the bubbles are subjected. In addition to this, the increased consistency of the ultra-lightweight cementitious paste allows to apply this special concrete through cutting-edge technology such as 3D printing, as illustrated on the slide. A more common strategy to increase compressive strength is to introduce silica fume in the mix proportion. This mineral addition gives rise to an improvement in compressive strength due to its smaller size than the cement particles and its pozzolanic activity. Given the potential of 3D printable lightweight foamed concrete, this comparison was carried out on foamed concrete pastes with the presence of viscosity enhancing agent. The comparative histogram shows a significant increase in the compressive strength of ultra-lightweight foamed concrete in all the curing conditions analyzed. In particular, there is an increase of about 157, 195, and 225% for air, cellophane, and water curing condition, respectively. As already said, in the field of foamed concrete, another fundamental parameter is the mixing process, in particular the kind of mixer and the mixing intensity. Indeed, in the relevant literature, it has been demonstrated that an increase of the mixing speed from 500 to 2000 revolutions per minute can lead to a decrease of the mean diameter of the bubbles of a foam of approximately 75%. As mentioned above, this positively affects all properties of foamed concrete. Therefore, an additional class of specimens were prepared with a mixing intensity of 3000 revolutions per minute. Also in this case, the comparison was carried out on 3D printable ultra-lightweight foamed concrete. The comparative histogram shows that passing from 1200 revolutions per minute to 3000 revolutions per minute in mixing intensity, there is an increase of 96, 104, and 36% for air, cellophane, and water curing condition respectively. Therefore, the increase of the mixing rotational speed represents a simple strategy to improve the compressive strength of ultra-lightweight formed concrete without further mineral or chemical additions. In conclusion, the utopia in the construction field is to realize a material characterized by lightness, very good mechanical properties, and excellent performance in terms of fire resistance and thermal insulation. In this contribution, 3 different strategies to improve the compressive strength of ultra-lightweight formed concrete through modification of its microstructure have been presented. Increase the consistency of fresh cement paste, add silica fume, increase the mixing intensity. Strategy 1 not only leads to an appreciable increase of the compressive strength in air and cellophane curing conditions, but also gives rise to a stabilization of lightweight cementitious system, allowing to exploit this interesting material through cutting-edge technologies, such as 3D printing. Strategy 2 is associated with the most important increase in the compressive strength of ultra-lightweight formed concrete, 192% on average over the 3 different curing conditions analyzed. Strategy 3 is characterized by an average increase in the compressive strength over the 3 different curing conditions of about 79%. The main advantage linked to this strategy is due to the fact that the improvement in the compressive strength is related only to a modification of the mixing phase and not to a mineral or chemical addition to the mix design of the cementitious material. Thanks for your attention.